Let's start with the basic idea. An interest rate swap is simply an agreement where one party pays fixed interest and receives floating interest. You can think of it like exchanging two types of loans. The fixed side behaves like a fixed coupon bond, and the floating side behaves like a floating rate note. So conceptually, a swap is just fixed bond minus floating bond. To price a swap, we break it into simple cash flows first. If you're paying fixed, you're committing to fixed coupons every year. That feels exactly like you issued a fixed rate bond. So paying fixed is basically like being short a fixed bond. Now look at the floating side. Here, the interest keeps resetting to market rates. Because the coupon adjusts constantly, floating bonds usually stay close to par, around 100. So instead of valuing every payment, we simply treat the floating leg as worth 100 today. So our job becomes much simpler now. First, we calculate the present value of each fixed payment. Second, we use those PVs to measure risk. And finally, we just add the floating leg value directly as 100. Let's plug in some numbers. Notional is $100 million. Fixed rate is 5%. Maturity is 4 years, and payments are annual. Discount rate is also 5%. So each year, fixed payment equals 5% of 100 million. That's 5 million per year. Now we discount each payment back to today. Year 1 becomes 4.76, year 2 becomes 4.54, year 3 becomes 4.32. In the last year, we receive 105 including principal, giving 86.38. Adding everything gives us roughly 100 million, so both fixed and floating legs are near par. Next, let's measure risk using VAR. We apply a VAR percentage shock to each present value. So 4.76 with 1% gives 0.048 risk. Similarly, we get 0.068, 0.086, and 2.59 for the last year. If we simply add all these risks together, we get the undiversified VAR. So 0.048 plus 0.068 plus 0.086 plus 2.09 equals 2.79 million. This assumes every maturity moves together. Basically, it's a worst-case scenario. But in reality, rates at different maturities don't move perfectly together. Some move more, some less. Because correlations are below 1, total risk actually reduces. So we use matrix math. VAR equals square root of 1 transpose sigma W. Here, our risk vector is 0.048, 0.068, 0.086, and 2.59. And we plug in the given correlation matrix between years 1 to 4. Using this matrix captures diversification effects automatically. This gives us a more realistic, and usually lower, portfolio VAR. Now we plug everything into the matrix formula to get the diversified risk. When we multiply the correlation matrix with our risk vector, we get new adjusted values, 0.6258, 0.912, 1.6884, and 2.6716. Next, we take the dot product with the original risk vector. So we calculate 0.6258 times 0.048 plus 0.912 times 0.068 plus 1.6884 times 0.086 plus 2.6716 times 2.59. This gives us 7.1567. Finally, we take the square root, and that gives 2.675 million. And that's our diversified VAR, which is lower than the undiversified 2.79 million, thanks to diversification. And that's exactly how swaps are broken into bonds, valued using present value, and then measured for risk using VAR. Simple steps, clean logic, no complicated tricks.